Okay, so we have started our discussion on concurrent processing, and in the last class we have discussed about one language structure, that is fork join structure. For expressing concurrency in a given program. Okay. Now there is another construct, language construct, which can also be used for writing concurrent programs, which is called co-begin, co-end construct. So to explain how this co-begin, co-end construct can be used for writing concurrent programs, let us take the same flowchart, the same precedence graph that we have considered in the last class. So in the last class, we have taken a precedence graph something like this. We have a number of statements, S1, S2, S3, then S4, S5, S6, so this is one of the precedence graphs that we had considered for writing a concurrent program using fork join structure. Now, using co-begin, co-end structure, if I want to translate this same precedence graph into a code, it should be executed, it should be written like this. First, you have to execute statement S1, because till now there is no concurrency. After that, we can have two processes, one process executing statement S2, the other process will execute statement S3. That means we have to create two processes for these two statements. In case of fork join structure, what we have done is we have written a fork statement, which is a system call, and the responsibility of the fork statement was the fork has to be written along with a level. Okay? So the responsibility of the fork statement is that the level that is mentioned, one process will start execution from the statement at that particular level, say L, and the other process will execute with the statements just following the fork statement. Okay? Now, in case of co-begin, co-end structure, to create two processes, we use a co-begin statement. So I have to have a structure, co-begin, and similarly I have to have a co-end structure, co-end statement. Okay. So if I have n number of statements within this co-begin, co-end structure, then it will create n number of processes. Okay. One process will be executing one statement within this co-begin, co-end structure. Okay. Now here we have two processes, one is S2, other one is S3. Okay. So what we'll do is, we'll create two processes. One process will execute statement S3, and the other process should execute statement S2. Okay. Now find that if we concentrate on this part of the precedence graph, okay, so I can say that after executing statement S1, I create two processes. One process should execute this part of the precedence graph, and the other process should execute S3. Okay. Now, when I come to this part of the precedence graph, firstly I have to execute S2, followed by creation of two processes. One process will execute S4, the other process will execute S5. After completion of both S4 and S5, S6 has to be executed by a single process. Okay. So for that, what we can do is, I can write another begin statement. So I have to have a begin end construct. So whatever you have within this begin and end construct, that becomes a single process. Okay. Now within this single process, I have to execute statement S2. So S2 will be executed under this. After completion of S2, I have to create two more processes. One will execute S4, the other one will execute S5. Okay. So I have to have another co-begin co-end construct. So under this, I'll put another co-begin and similarly co-end. Under this co-begin co-end, I have to have two statements. One is S4, other one is S5. So that means following this co-begin co-end structure, two processes will be created. One will execute S4 and other one will execute S5. Okay. So after completion of this S4 and S5, then you have to execute statement number S6, and S6 has to be executed by a single process. Okay. So you find that how we have translated this precedence graph into a program like this. First, we are executing S1 by a single process. After completion of S1, we are creating two processes. One process will execute S3 and other process will execute the statements which are within the begin end structure. Okay. Now under this begin end structure, so this process, the process which is executing this part of the code, that is responsible for this part of the precedence graph. Here, first we have to execute S2. After S2, we have to create two processes. So I put co-begin co-end structure, and within this co-begin co-end, I have two statements, S4 and S5. So there will be two processes created. One process will execute S4, other one will execute S5. Okay. When both these processes are terminated, they complete their operation, then the parent process which has created these two processes, that will execute S6. Okay. So at the end of this, you find that S2, S4, S5, these executions will be complete. Okay. Now when you come out of this first co-begin co-end construct, so that ensures that all these operations, all these processes for S2, S3, S4, S5 and S6, they have completed their operation. Okay. So after these processes complete their operation, the last statement has to be executed by the parent process of all of them, and that will execute statement number S7. Okay. And this whole thing I can put under a begin end construct. Okay. So with this example, you find that writing, given a precedence graph, writing a co-begin co-end construct, language construct for that precedence graph is very simple. Okay. So if at any place we have to create the n processes, each of the process will execute some statements, then what we'll do is we'll put all those statements under co-begin co-end construct. So if I have, say, 5 statements within a co-begin co-end construct, that means 5 different processes will be created. If you have 3 statements, that means 3 different processes will be created. Okay. So that is how we can translate the precedence graph in a co-begin co-end construct language. Okay. Now there is a marked difference between the fork join structure and the co-begin co-end structure. In case of fork join structure, what we have said is let us look at that previous example here. It is the same precedence graph. Okay. So in case of fork join structure, what we have seen is that whenever a process has to be created, then you use a fork statement with level L1. So I create two processes. One process starts execution from level L1. The other process starts execution with the statement just following this fork statement. Okay. Now when these two are to be joined, that means I want to have a single process which will continue with the rest of the operation. Then I use this join statement. Join with count, where this count indicates that how many processes are to be joined at this point. Okay. And the process which survives after computation of this join statement, that continues with the next statement. Okay. Now here it is not ensured that whether the child process will continue the next statement, that is whether the child process will survive or the parent process will survive. Any of them can survive depending upon which one executes this join statement last. Okay. In case of co-begin coend, the situation is different. Here we have distinct parent processes and distinct child processes. Okay. So when I start this begin end, the first begin end, we create a parent process. That is a single process. The parent process executes statements S1. Okay. After execution of statement S1, the parent process finds a co-begin coend structure. Okay. When it finds this co-begin coend structure, it creates the required number of child processes. In this case, there will be two child processes. One child process will execute statement number S3, and the other child process will execute the statements within this begin end structure. Okay, because this begin end says that this part has to be sequential. Right? So, two child processes are created, and these two child processes will start execution of their statements concurrently. What will the parent process do during that time? In case of fork join structure, we have seen that both the parent process and the child process, they execute concurrently. But in this case, the parent process, after creation of two child processes, will wait until and unless all the created child processes terminate. Okay. So when all the created child processes will finish their operation and they will terminate, then again the parent process will wake up and the last statement, that is S7, will be executed by the parent process. Okay. But in case of fork join structure, we have seen that we cannot ascertain that S7 will be executed by the parent process or S7 will be executed by the child process. But in this case, it is sure that this S7 will be executed by the parent process only. Okay. Similarly, within this begin end structure, the child process which is executing this begin end structure, that will be the parent of two processes executing S4 and S5. Okay. So only when S4 and S5, so after creation of S4 and S5, two processes executing S4 and S5, the child process which has created these two processes will go to sleep mode. Okay. When both S4 and S5 are complete, then only this child process will wake up again and that will execute S6. Okay. So we can ascertain that this sequential nature, the sequential part of the program, is always executed by the parent process, which is not ensured in case of fork join structure. Okay. So we have two different constructs. One is fork join construct, and other one is co-begin coend structure, co-begin coend construct. Now, naturally, a question arises that are both of them equivalent? I mean, other than whether the child process continues execution or the parent process continues execution. That is, given any precedence graph, whether we can write concurrent programs using fork join structure as well as co-begin co-end structure. Okay. So for that, let us take a particular flow graph or precedence graph. So I take a precedence graph, a variation of the precedence graph that we had taken earlier. That is the first example that we considered while writing this. So this is the first precedence graph that we had considered for writing a concurrent program using fork join structure. And we have seen that this precedence graph can be easily converted into a parallel program using fork join structure, and that fork join structure program was this. Okay. Now if I take a variation of this precedence graph, okay, so I'll make slight modification. Now I'll consider a precedence graph like this. S1, S2, S3, S4, S5, S6, and S7. So the precedence relation is like this. Okay. So you see that I have made slight modification. Earlier our precedence relation was that S7 depends upon S3. S6 does not depend upon S3. Okay. Here I make a modification that I have made S6 also dependent upon S3. Okay. Now with this, even if I have a directed edge from S3 to S7, that does not change the nature of this precedence graph, because that becomes redundant. Since S7 depends upon S6, that is S7 cannot be executed unless S6 is complete, and S6 cannot be executed unless S3 is complete. So even if I make a directed edge from S3 to S7, that becomes redundant, because anyway, since S7 depends upon S6 and S6 depends upon S3, so obviously S7 depends upon S3. So this directed edge will be redundant. So this is an additional precedence relation that I have put, that S6 also depends upon S3. Okay. So for this precedence graph, you will find that we can easily write a fork join structure to translate this into concurrent program. Okay. You take this as an exercise. And if you try to write a co-begin co-end structure to translate this into a concurrent program, you will find that you cannot write a co-begin co-end structure. Okay. So this can be easily converted into fork join structure, but this cannot be converted into co-begin co-end structure. So that is why we can say that fork join structure is more powerful than co-begin co-end structure. Any type of precedence graph can be converted into fork join program, but it may not be possible to convert that into co-begin co-end program. Okay. So this you take as an exercise. Now let us come to a conceptual problem. I mean, it's a classical problem which is always discussed in operating system, which is called a producer-consumer problem. Now the producer-consumer problem is something like this. We have two processes. One process is called producer P. We have another process which is a consumer process or C. Okay. The idea is like this, that producer process produces some items which are to be consumed by the consumer process C. Okay. So the items which are produced by the producer process, those items should go to the consumer process, and the consumer process will consume the items. Okay. The producer process is an independent process. We would like to have that producer process should be able to generate items independently of the consumer. We would also like to have a situation that the consumer process will also be able to consume the items independent of the producer. Okay, so that these two processes can run concurrently. Now, if I have this type of situation, in that case, we won't have any problem if the rate at which the producer process generates the items or produces the items is same as the rate at which the consumer process can consume the items. Okay? If the producer process produces items at a faster rate than the rate at which the consumer can consume the items, then naturally some of the items will be lost. Okay? On the other hand, if the consumer process can consume at a faster rate than the rate at which the items can be produced, then consumer process will have to wait for availability of the items. Okay. A typical example of this producer-consumer process is the printer. We can say that the computer is the producer because whenever we want to take printouts of some file, it is the computer which sends the data to the printer and the printer prints that data file. Okay. So you can say that computer in that case is a producer and the printer is a consumer. So the computer is producing the items or producing the characters, sending them to the printer, which is the consumer. Okay. And the printer consumes the items in the form of giving you the final output. Okay. Now, if the rate at which the computer can generate or send the data or send the characters, if the printer can also print out those characters at the same rate, then I don't have any problem. But usually that is not the case. Usually, the computer sends out the data at a rate which is faster than the rate at which the data can be printed. Okay. So unless I take some extra precaution to take care of this speed mismatch, in that case, it is quite natural that some of the data will be lost. The printer will not be able to print them. Okay. So a natural solution is, in between the producer and consumer, you have some buffer. So the concept will be like this. I have producer process. I have consumer process. Now, instead of directly sending the data from the producer to the consumer, in between producer and consumer, you have some buffer pool. So the producer will produce the items and put them in the buffer pool or array of buffers, and consumer will consume the items from the buffer. Okay. So in this case, even if the consumption rate of the consumer is less than the production rate of the producer, there should not be any problem because the producer will produce the items and put in the buffer. And consumers, whenever it needs an item, it will consume the item from the buffer. Okay. So this is the buffer pool. Now, even in this case, we can have two types of situations. One is unbounded buffer. That is, we don't have any limitation on the buffer size. So we call it unbounded buffer. And the second case is naturally is the bounded buffer case. So you see that if we have unbounded buffer, then practically we don't face any problem, because at whatever rate the producer produces the items, there is always some space in the buffer to put that item. But if we have bounded buffer, in that case, since our assumption is the production rate is higher than the consumption rate, so naturally the buffer is going to be filled up, because there will always be some items accumulated in the buffer. And if we have bounded buffer, then there will be a point of time when all the locations in the buffer will be full. So if the producer produces an item, there is no space in the buffer for that item to be placed. That means the producer has to wait until and unless some item is consumed from the buffer by the consumer, and that location in the buffer is left free where the new item can be put by the producer. Okay. So that is the waiting that has to be done on part of the producer. Okay. In case of consumer, if the rate of production is less than the rate of consumption, then the consumer at some point of time will find the buffer to be empty. So if the buffer is empty, obviously the consumer cannot consume any item from the buffer, so the consumer has to wait until and unless the producer produces some item and places in the buffer, which the consumer can subsequently consume. Okay. So these are the problems that we'll face in case of bounded buffer problem. Obviously, of course, even in case of unbounded buffer problem, the consumer may have to wait if the rate of consumption is higher than the rate of production. But for unbounded buffer, the producer will not have to wait, because the producer will always find some empty space where the new item can be placed. Okay. In case of bounded buffer, the producer may have to wait, as well as the consumer also may have to wait. Okay. So given such a type of problem, let us see that how this kind of problem can be translated into a code using the co-begin co-end structure. So we'll write the code like this. We'll assume that there are two processes. One is producer process and other one is consumer process running concurrently. So they can be placed under a co-begin co-end construct. Okay. So before that, let us see what are the variables that we'll need. We'll declare a type, say item. Okay. So you can define some type, which is a variable type. So the producer will produce an item of type item. Similarly, whenever the consumer consumes an item, that will consume an item of type item. Okay. Then the variables that we need are we have to have a buffer, and we assume that it's a buffer having n number of locations. Okay. So we'll declare this buffer as an array of 0 to n minus 1. So 0 to n minus 1 total is n number of locations of type item. Okay. We know we need 2 pointers or 2 indices to point to an item in the buffer, because buffer is an array. So I must have pointers which will point to different items in the buffer or different locations in the buffer. So we'll have 2 pointers. One is pointer in and other one is pointer out. Okay. And these pointers, because there are n number of locations numbering 0 to n minus 1, So obviously this pointers also will assume values, can assume values from 0 to n minus 1. So we'll write like this, 0 to n minus 1. Okay? And we use two more variables. One is next p and other one is next c of type item. Okay. So our assumption is whenever the producer produces an item, the item is assigned to next p. Okay. Then from next p, it will be loaded into the buffer when some location in the buffer is free. Similarly, when the consumer consumes an item, it takes out an item from the buffer, puts that item into next c, and subsequently the consumer will consume it. Okay? And we'll initialize in to 0, out also to 0. Okay. So the buffering concept that we will use in this case, we'll assume that it's a circular buffer. And those who have attended the last lecture on data structure, they know what is a circular buffer. Okay. It is not physically circular, it is linear, but logically we use a circular by making increments on this pointers in and out using modular arithmetic. Okay. Now, once these variables are declared, now we can write codes for the producer process and the consumer process. The codes will be something like this. It will be placed under co-begin and co-end structure. So we'll put as co-begin. Under co-begin, let us first write the code for the producer process. So this will be the code of the producer process. Okay. So the producer process produces an item, and as we said that the item is placed in variable next p. Okay. So after that, the producer process will check whether there is any vacant space in the buffer or not. Okay. And you find that when the buffer is full, the condition will be in plus 1 mod n equal to out. Okay, so when this condition is true, that means there is no empty space in the buffer when this new item can be placed. So the producer process will remain in this while loop. Skip means doing nothing. It simply goes on executing this while loop. Okay. When this condition is broken, that is while loop is broken, it comes to the next step, places the item into the buffer at location in. Okay. And after that, in is incremented by 1 following modulo arithmetic, and that gives it the circular buffer nature.
We are not incrementing the value of in the while loop, then how can it break?
If the consumer process consumes an item, okay, in that case value of out will be changed, right? So that is the code for the producer process. Similarly, we can write the code for the consumer process, and which will look like this. And then we'll put co-end structure. Okay. So we have co-begin here and co-end here. Okay. So these two, producer and consumer processes, they are under the same co-begin co-end structure. So in case of consumer process, again it finds, checks whether in is equal to out or not. So if in is equal to out, that is a condition that the buffer is empty. So when the buffer is empty, obviously there is no item in the buffer which the consumer can consume, so the consumer process will wait in this while loop. Okay. When in is not equal to out, that means there is some item in the buffer which the consumer can consume, so it takes that item from the buffer following the out pointer into variable next C, and it modifies this pointer out. So that is why this while loop in the producer process will be broken. Okay. Similarly, in equal to out, this condition will also be broken by the producer process. If the producer produces an item and puts into the buffer, then this condition will be false. Okay. So after that, the consumer will consume the item in the next C in its own time, and you find that this producer and consumer both these processes has been kept under repeat until false structure. So we assume that the producer process goes on indefinitely, the consumer process also goes on indefinitely. Okay, producer process goes on producing items, putting them into the buffer whenever some location in the buffer is free. Similarly, consumer process goes on consumes items from the buffer whenever there is some item in the buffer. Okay. So with this you find that this producer and consumer process, writing that in the form of a co-begin co-end construct, is very simple. However, if you study this algorithm, you will find that there is a flaw in this algorithm. What is that flaw? The flaw is in this condition checking. The way we are checking the condition, you will find that there must be one location always free. So even if I have n locations within the buffer, I cannot fill up all the n locations in the buffer with the items. Okay, at least one location must be free. So if I want to make use of that one location also, that means because I have n number of locations in the buffer, I want to give freedom to the producer that it can produce the items. Even if the consumer is off, the consumer is not consuming the items, the producer should be able to produce n number of items and fill up all the locations in the buffer. Okay, so if I want to do that, then obviously this algorithm will not help. So what can be done is, in addition to using these in and out pointers, we can have a counter. Okay, so responsibility of the producer will be to increment the count whenever it puts an item into the buffer, and the counter will be decremented by the consumer whenever the consumer consumes an item from the buffer. Okay, and the counter is initially 0. So at any instant, the value of the counter will indicate that how many items are present in the buffer at that particular instant of time. Okay. So the producer process will check whether the counter value is equal to n or not. Counter value equal to n means n number of items are present in the buffer. So if value of the counter equal to n, the producer will wait. If it is less than n, it will put the item into the buffer and increment the count by 1. Similarly, the consumer process will check whether the count value is equal to 0 or not. If it is 0, then obviously the buffer is empty. The consumer cannot consume any item and it has to wait. When the count value is greater than 0, then only there is some item into the buffer which the consumer can consume. Okay. So after consuming the item, the consumer will reduce the value of count by 1. Okay. So with that modification in this code, we can make use of all the n locations in the buffer. Okay. So to make use of that, what we have to do is we have to make a very simple modification. That is, here instead of checking while in plus 1 mod n equal to out, what we do is we have to do here, what we have to check is while counter, let me put it here, while counter or say count equal to n, do skip. Okay. So this is the statement which will replace this statement. That means if count equal to n, then obviously all the n locations in the buffer are full, so the producer process cannot put a new item into the buffer. Okay. If count is not equal to n, which is less than n, then it puts the element into the buffer, increments the in pointer as it is. In addition to this, the other task it has to perform is increment the value of count by 1. So it has to make count equal to count plus 1. So that has to be inserted here, and this will replace this statement. Our assumption is initially the value of count is equal to 0. Similarly, for the consumer process, what we have to do is, instead of checking while in equal to out, we have to check while count equal to 0. So this will replace this statement. Okay. Then others will remain as it is. And what additional statement we have to insert is, because now the consumer is consuming an item from the buffer, so it has to decrement the value of the count. So it has to make count is equal to count minus 1. So this statement has to be inserted here. Okay. And in addition, during the variable declaration, obviously we have to declare the count and initialize the value of count to 0. So if I make this slight modification, then you see that we can make use of all the n locations in the buffer. That means the producer can produce n items and place all the n items into the buffer. Okay. However, still this algorithm is not problem free. We'll see in the next class that what is the problem that you can face using this algorithm.
This is the repeat statement given after begin. So why is it the repeat statement?
That is the repeat until. Repeat until statement. And what is the purpose of repeat until? Until and unless the condition is true, it will continue. So we have made it forcibly false. Repeat until false. That means it's an indefinite process. And begin end indicates that that part is sequential. Producer is a sequential process. Consumer is also a sequential process. These two sequential processes are kept under co-begin co-end. Okay. So producer is a sequential process. Consumer is also a sequential process. And these two are concurrent. Right?